Hey everyone. So thanks for the invitation. So I'm going to talk about, as Monroe said, restrictions of Todorcevic's OCA with large continuum. So let me start with the basic definitions. So this is Todorcevic's OCA. It's a very simple statement. It's a statement that every open graph on a separable metric space is either countably chromatic or has an uncountable clique. And this is obviously a dichotomy, right? I mean, you cannot be both countably chromatic and have an uncountable clique. And it's saying that really the only obstacle for being countably chromatic is having an uncountable clique. I'm talking here about separable metric spaces, but you might as well assume the space is a subset of the real numbers. I mean, there is no loss of generality. So with the topology induced from the real numbers. So this is OCA. It's not clear why it's talking about an open coloring, right? The name of the axiom. So there is an alternative phrasing where you look at the characteristic function of the graph, right? So think of chi here as a characteristic function of a graph. So it's a coloring from pairs into 0, 1, 0 if the pair is a vertex in the graph, 1 if it's not. The graph is open just in case that the preimage of 0 is open. So that's what Todorcevic called an open coloring. And then the axiom says that either X can be partitioned into countably many one-homogeneous sets. So one homogeneous is a set where no two things are connected, so it's one colorable. So this is being countably chromatic, right? Partitioned into countably many one-homogeneous sets. Or the alternative is having an uncountable zero homogeneous sets. And zero homogeneous means any two things are connected in the graph, so that's a clique. So those two statements are equivalent, and here I'm just saying that the way to see the equivalent is to view chi as a characteristic function of a graph. Okay, so and this is OCA. So the axiom was introduced by Todorcevic in the late 1980s. He showed it's consistent. He had some applications. It's not only consistent, it's in fact the consequence of PFA. Now, forcing PFA requires large cardinals, but OCA can be forced directly without any large cardinals. Now, OCA is really a central statement in set theory. It has many, many interesting applications. It's one of the central and most important consequences of PFA. And central in the sense that it itself, so it's a consequence of PFA and it itself has very important consequences. One consequence is it implies the continuum is at least Aleph2. And the known consistency proofs for OCA all lead to models where the consistency is where the continuum is exactly Aleph2. For example, if you go through the route of getting PFA, the continuum would be Aleph2, but any other known way to force it gives the continuum is Aleph2. And this, of course, leads to the natural question, is it consistent with the continuum being greater than Aleph2? I mean, it's interesting in its own right? It's interesting to know what consequences of PFA are consistent with a large continuum. It's also interesting because of the applications, right? So you get ways to get all these applications with a large continuum. I mean, one way to get all of them. So I won't keep the suspense. So this question is still open, right? And I'm not going to talk about solving this question here, but I am going to talk about some restrictions of OCA that are consistent with a large continuum. Before I do that, let me give a few related results. First, the definition about the restriction. So OCA kappa is the restriction of OCA to spaces of size kappa. If kappa is a continuum, then this is just a full OCA, right? I mean, any space that is relevant for OCA is a set of real numbers. So it has size at most a continuum. So OCA, the continuum is just OCA. So kappa here is typically smaller than the continuum, right? A little bit more notation by OCA less than kappa, I mean a restriction to spaces of size less than kappa. And OCA less than C is the restriction to all spaces of size less than the continuum. Right? So you just rule out spaces that actually have the same size as the continuum, you allow anything smaller. Okay, so the first partial result is that OCA aleph 1 is consistent with arbitrarily large value for the continuum. This is due to Farah. It's unpublished. I don't know the exact time. Maybe about 20 years ago. I'm not completely sure. For another partial result, I need to introduce another coloring axiom. So this was defined by Abraham Rubin Shelah. The paper was published in 1985. This is defined directly with colorings. So you have chi, which is a coloring into 0, 1, although any finite coloring will do. X here is a subset of R of size aleph 1, so there is built-in a size restriction. And the coloring, both the preimage of 0 and the preimage of 1 are open. So the axiom says that in this case, you can not only find homogeneous sets, but you can actually partition the space into countably many homogeneous sets. And they can be homogeneous for either 0 or 1. Together, they cover the whole space. The reason I'm mentioning this coloring axiom is the following results of Justin Moore, that if you combine these two coloring axioms, the Todorcevic and the Abraham Rubin Shelah axiom, then together they do imply that the continuum is exactly aleph 2. So this is another partial result towards the question of whether OCA Todorcevic implies the continuum is aleph 2. And it becomes even more relevant towards the question of whether OCA, so first, one other thing, Moore doesn't, just a note, a comment, so Moore doesn't really use the full force of OCA Todorcevic, he just uses a couple of consequences. One is just the restriction of OCA Todorcevic to spaces of size aleph 2, and the other is the consequence that B is less than or equal to aleph 2. So you can find an unbounded family of size aleph 2. In fact, an unbounded chain of size aleph 2. Now, so you look at Moore's results. I mean, so it's not clear whether you're talking about the conjunction of the two axioms together implying the continuum is aleph 2, or maybe just one of them implies the continuum is aleph 2. Right? If it's just one of them, it would have to be OCA Todorcevic. This is because of the following result of myself and Thomas Gilton, that OCA Abraham Rubin Shelah by itself does not imply the continuum is aleph 2. It is consistent with the continuum is equal to aleph 3. So this raises the stakes on the question of whether OCA Todorcevic implies the continuum is aleph 2. And in fact, not even the full OCA Todorcevic, just these two consequences, B less than or equal to aleph 2, and OCA Todorcevic for spaces of size aleph 2. So the question here is whether even just these two consequences imply that the continuum is aleph 2. And the answer to that is no. Okay, so this is the question. The answer to that is no, and this will be a consequence of what I'm going to sketch today. Before I do that, I just want to comment, this is one step above Farah's result, right? Farah's result was OCA for spaces of size aleph 1. This is one cardinal above, so spaces of size aleph 2. So of course it's been open when Moore got his result. Okay, so the answer is no. In fact, you can get not just OCA for spaces of size aleph 2, but OCA for space of any size less than the continuum with arbitrarily large continuum. Okay, so that's a theorem. I'm assuming a Malo cardinal here. Then you can get OCA less than C with arbitrarily large continuum. And you get that B is equal to aleph 2 in all these models. Okay, so Moore's result would apply in these models if they satisfied OCA ARS, which of course means that they do not, right? So I guess it's showing that Moore's result really requires the conjunction of the two things, right? Neither one of them individually would prove the continuum is Aleph 2. The real question, of course, is whether OCA, the full OCA, is consistent with the continuum being greater than Aleph 2. This is still open for now. And it's not clear that the methods I'm using for my theorem would actually, that there would be a way to push them further for the full OCA Todorcevic. At least for now, it doesn't seem like it. Okay. And then the rest of the time, I want to talk a little bit about the proof. Before I get to OCA with large continuum, let me talk about just the consistency proof of OCA itself. And let me just do one step. So let's fix an open graph G on a set X containing R and assume that G is not countably chromatic. What we need to do is we need to force an uncountable clique. Okay? And then more than that, we need to iterate that forcing until we reach OCA Todorcevic. So I'm going to do it in several steps. The way I do it has a lot of redundant steps, right? I mean, you could do, if you're interested in just OCA, you could do things with a lot less forcing than I'm doing. But I'm doing it this way to set things up for then revising the proof to get larger continuum, right? So the first step is to add a subset of the graph, enumerate it. This should be omega 1 here, not omega. So let me see if I can fix it. So this is omega 1. So the first step is to add a subset of the graph enumerated in order type omega 1. And then we'll concentrate in adding on a clique. We'll concentrate on adding a clique that's contained in this initial subset that we're adding. Now, this initial subset will be added with countable conditions. The countable conditions are countable initial segments with certain commitments. And what are the commitments? The commitments are certain one-colorable sets that we need to stay out of. So a commitment is a sequence of one-colorable sets. And once I made the commitment, I require that from now on, every new x psi has to be outside the countable, the one colorable sets listed before psi. So this is a commitment. I'm committed to being outside certain one colorable sets. Why can I commit this? So why can I even find an x psi which is outside all these one colorable sets? This is because of the assumption that the graph is not countably chromatic, right? So I have at any stage, I have countably many commitments. Each commitment gives me countably many one colorable sets to stay out of. It's countably many altogether, and there will be nodes outside these countably many one colorable sets. So this is the first step, and this is a countably closed forcing. One other comment, I could have just as well required these one colorable sets to be closed. This is because the closure of the one colorable set is still one colorable and bigger. So if you stay out of the closure, you stay out of the original set, right? And the closure is still one colorable because the graph is open, right? So without loss of generality, I could have just as well required all the C etas to be closed. Okay, so that's the first forcing step. The next one is to force a fast club. This is still a countably closed forcing. And then divide my set of nodes, the x size, into intervals partitioned by the club, right? So the iota interval is everything between enumerated by ordinals between the iota point in the club and the iota plus first point in the club, right? So you look at the club, you look at the iota point, the iota plus first, you look between them and you just take those nodes. So this is I iota. The nodes enumerated by psi between the iota and iota plus first point in the club. Okay, and now comes the real step, and this will not be countably closed. And this is now to force with finite cliques. They have to be contained in the set that we set up before, right? The specific set of nodes that we picked up ahead of time. And more than that, they have to pick just 1 point, I mean, at most 1 point in each of those club intervals. So this is the forcing, force with finite conditions to add a clique contained in the points we already picked up, with just 1 point, at most 1 point in each interval. And the really beautiful thing about this is that this will be CCC. I don't have time to go into the proof of that. It's a very beautiful proof due to Todorcevic. Very roughly speaking, if you had an anti-chain, being an anti-chain means incompatibility. So it means that various things that are one-colorable, right? They're not connected in the graph. So you could take the closure of the anti-chain that would still be an anti-chain. And then somehow using the fact that we avoided so many one-colorable sets, you could take a condition in the closure of the anti-chain that sits high enough in those intervals and somehow convert it into 2 compatible conditions still in the closure of the anti-chain, and that would be a contradiction. So I can't say more, but it's a very, very beautiful argument. And that finishes the proof. I mean, that forcing with the clique will add an uncountable clique. I mean, there is a slight wrinkle. You might have to drop a countable initial segment of your club just to avoid some trivialities. But this will add an uncountable clique. And it does it with a countably closed forcing followed by CCC. So this you can iterate, it's proper. Or you could just do all the countably closed things ahead of time as a kind of preparation and then do the CCC. That's also an option. Okay. Now, I want to note that the initial forcing will probably collapse X to size Aleph1. Right? I mean, you're adding a subset of X with countable conditions. Most likely X will be collapsed to size Aleph1. And this is why it's hard to get OCA with large spaces without ending up with continuum being equal to Aleph2. Because I mean, think of the space X as being very large, you'll probably collapse it to Aleph1. And you keep iterating that, you'll probably collapse along the way anything smaller than the continuum to size Aleph1. Okay, so now let's try to see how we can do it in a way that will not collapse the continuum, anything smaller than the continuum to size Aleph1. And let me again do one step. So I want to try to repeat the same argument, but without collapsing the space to size Aleph1. Right? So I'll do a little bit of preparation. I'll assume GCH to start. Then I'm going to add delta coin subsets of omega1. And the key point of that is that it's adding a lot of almost disjoint subsets of omega1. I'll call them in nu. This is for nu less than delta. So think of delta as very large. This is our eventual size of the continuum. So the first thing I do is I have delta almost disjoint subsets of omega1. Okay. And let's just call the resulting model V, right? So V is something we obtained by starting with GCH and then adding a lot of almost disjoint subsets of omega1. Okay, so of course it will not satisfy the GCH anymore. The power set of omega1 will be delta, right? But that's fine. Then over V, I'm going to force to add a lot of coin reals, so delta coin reals. This is just a quick way to ensure that the continuum is going to be delta, right? So I'm going to end up with a large continuum, provided I do not collapse below delta, right? Provided I keep delta large. Now let's take a lot of open graphs on a lot of spaces. So the open graphs are all named by the same G dot. That's just naming using just one coin reel, but I'm interpreting them using all my different coin reels. So I have delta graphs here, and I also want delta spaces. They have different names and they use all the coin reels, right? And let's suppose they're all not countably chromatic. And I want something similar to the previous argument, but I want to simultaneously handle all these graphs, right? So I don't want to do them one by one. Because when I do them one by one, I might kill one of them, right? I might suddenly do one of them and then that would color another one, and then I don't do the other one anymore. And here I want to do all of them, and I want to do all of them simultaneously. And I want to do it without collapsing the size of the space. Right? So this is my goal for the one-step argument. There is a simple way to avoid collapsing the size of the space, and this is to take a column hole of size aleph1 with the name for the space in it, and then just take all my points from that column hole. So now I'm not collapsing the space. I would be collapsing the space intersected with this column hole, but that already has size aleph1 because my column hole has size aleph1. Right? So I'm going to try to repeat the previous argument, but add my points just from that column hole, and then nothing will be collapsed. The commitments would be as before, but I want to point out that the commitments do not come from this column hole. I'm going to have to make sure that my forcing is CCC over the entire universe. And that means that the commitments need to involve uncountable sets that possibly are not named inside this column hole, right? So the commitments still use everything, but the points will need to come from this column hole. This, of course, raises a very quick question. I need to know that if I have countably many commitments that may not come from this column hole, I can still find a point inside this column hole that avoids all of them. Before that wasn't an issue. I had the whole space at my disposal. The countably many uncountable set couldn't color the whole space. I could find a point outside them. But here, if the countably many commitments just color this column hole, I'm in trouble, right? So I will have to show that they do not color this column hole. But let me leave this for later. Okay, so this is what we have so far. We have our almost shown subsets of aleph1. We had delta coin reals to quickly raise a continuum to size delta. We're working with delta graphs and delta spaces, and we want to handle all of them simultaneously. And we restrict our points for each space to a column hole of size aleph1 to ensure we do not collapse the size of the space. Okay. Now do the next step. Just as in the one step for OCA, we force a fast club. And all this, by the way, is done without looking at the coin reals R, right? So I'm just doing a kind of term space forcing for adding the points, adding the fast club. So this is all countably closed over V. Now let's introduce the coin reals R. And again, let's look at the intervals, right? So I take the points that I added, I divide them to intervals based on the fast club. Right? So the iota interval consists of the points indexed by psi between the iota point of the club and the iota plus first. So just as before, and I'm doing it for each of my spaces. And now, just as before, I'll force to add a clique with finite conditions. So let's call that P new. So this will be the forcing to add a clique with finite conditions in the points I added for the new space. Again, picking just one point, at most one point for each interval of the club. But now more than that, and this is where I'm using the almost disjoint sets. For the new space, I will only use the club intervals that are indexed by iota inside the new almost disjoint set, right? So if you think of this, what I'm doing is I'm taking all these forcing P new and I'm separating them, right? Each one lives on a certain almost disjoint set in those club intervals. And that means that if you take any two of them or even any countably many of those forcing P news, eventually dropping an initial segment, they will live in completely different intervals of the club, right? So they will, each of them select at most one point from each interval, and no two of them will select a point from the same interval. And this lets you show that the finite, that not only that each of them is CCC, this would just be the same as the regular, the OCA argument, but the whole finite support product is CCC. And it's really the same argument, more or less. I mean, you will work assuming there is an anti-chain, you will do some kind of argument to produce two compatible conditions in the closure of the anti-chain. And it would be essentially the same argument. You'd work with some condition, you'd work with the points, and you'd do for each point in the condition, you do some kind of reflection argument to get two compatible points that reflects a lot of properties of that point. So, and you can still work point by point, because in each interval of the club, you still have just one point, and it comes from just one of the forcing. It might be different forcings for different intervals of the clubs, but that ends up not mattering. What matters is that in each interval, you still have just one point to worry about. And this is a crucial use here of the almost disjoint subsets that I added ahead of time. So this is the one step, and it would add uncountable cliques in all the spaces simultaneously. But I still owe you this point that I can meet the commitments inside this column hole. So let me quickly try to go over that. So you can assume the uncountable sets are closed. That means that each one of them depends only on a countable part of my list of coin reals, right? Because a name for a closed set will have some countable support in the forcing that adds the coin reals. So I can find a countable subset of delta A. Let's say it has order type row, and I can find names that refer just to row coin reals, right? So those d dot i's are just in the poset to add row coin reals, and my countable my closed uncountable sets are just interpretations of these names, the d dot I, using just the restriction of the coin reals to A, right? So I'm just using countably many coin reals here to get all the uncountable sets. So the entire sequence of named DIs is coded by a real in V, so it belongs to my column hole. Now, if I cannot meet all these commitments, if I cannot avoid all those uncountable sets inside this column hole, then each element of this column hole can be forced to belong to one of those uncountable sets, right? I'm just rephrasing the statement of star failing. And now I'm going to use homogeneity. So I can use the symmetry of the coin forcing under permutation of delta to replace this countable set A with any other countable set of my choice, provided I can find a permutation of delta that would map A to B and will not affect the members of the space. Right? Because, I mean, if I affect the member of the space, then this part of the statement that I don't meet the members of the space will also be changed by the permutation. But if my permutation doesn't affect the members of the space, then I can send A to B and preserve this statement that the members of the space are still forced outside the uncountable sets, now interpreted using B instead of A. And I can actually find such a permutation, so that will send A to B to some B and will not affect the members of the space. Well, I'm cheating a little bit. I can't do it for all of A. So I need to divide A into a part that's already in this column hole and the part that's outside. And really, I just shift the parts that's outside. But let's, without loss of generality, assume all of A is outside this column hole. That's a complicated situation. So I can find a permutation that moves it into this column hole and does not change any of the elements of the space in this column hole. And this is where I'm using the fact that the space has size less than delta. Right? And that means that the space itself only uses support in the coin forcing of size less than delta. So there are plenty of things I can do outside the supports of the coin forcing used for the space, plenty of things I can do there that will just not affect the interpretation of any elements of the space. And this is really a crucial point. I would not be able to do that if the space itself used all of the coin reals for its support. So it's really important here that the space uses fewer than delta coin reals for its support. So then I can shift A into the column hole, into H nu, without changing the space, so while preserving this statement. And then what happens is that now I cover everything in the space using colorable sets that are in the space. And now I get a contradiction, because this means by elementarity that these sets in fact cover the whole space, not just the space intersected this column hole. Or if there is inside this column hole a covering of the space intersected with this column hole, by elementarity this covering covers the whole space. And that's impossible, because supposedly the space is not countably, the graph is not countably chromatic. Right, so this is what I owed you before. And this completes the one-step proof or sketch. Now I can just repeat this thing, right? I just keep doing this, going over all colorings and all spaces until I reach some closure point where I have ACA and the continuum is the OCA for spaces of size less than delta, and the continuum is delta. So each step is similar to what I sketched above. The only difference is that I'm replacing the co-enforcing, which was a quick way to increase the continuum. I'm replacing it with the previous clique forcings. I mean, with co-enforces followed by the previous clique forcings, right? So I keep accumulating more and more clique forcings, and they all go into this, what was just coin in the initial step. This doesn't change that much. What did I use about co-enforcing? I used symmetry under permutations. This is preserved, and the way to preserve that is to make sure that in each step, I do simultaneously a collection of spaces and graphs that is closed under permutations. This is why I wanted to do a lot of graphs and a lot of spaces simultaneously, because this allows me to make sure that I do not just G dot, but all the permutations of G dot all at the same time, and this preserves symmetry. But one thing does change. Co-enforcing has size aleph 0. The clique forcings, even the first one, will have size aleph 1. So I'm losing the fact that my initial forcing was small. As I lose that fact, I will also lose the fact that I could internalize, that my supports that I try to internalize, the A that I try to shift to B, it was countable because for co-enforcing was countable, and I could name closed sets using just countable supports. But now with bigger forcings, I need bigger A's to name closed sets. So I need to internalize larger sets of supports. And to do that, I need larger column holes, right? So this is what I'm losing. The column holes now cannot just all have size aleph 1. At each step, I need a column hole that's larger than the supports I used. And the supports have size my previous column holes, right? Which in turn had to be larger than the previous supports. So those sizes keep increasing. The next step, I will need holes of size aleph 2. The step after that, I will need holes of size aleph 3, and so on. And this is where the Malo cardinal comes in. As the size increases, I have to allow holes of bigger sizes, and I end up collapsing those sizes, right? If I restrict my space to a set of size aleph 3, then I force with my countable conditions, I will collapse that size. I'll collapse aleph 3. So that's fine. I just keep collapsing. And when I do Malo many steps and collapse everything below the Malo to aleph 1, I'll reach my closure point where I got OCA less than delta. The continuum is delta. Delta itself is not collapsed. It should have been much larger than the Malo. And I'll end up with OCA less than C and the continuum large. That's a sketch of the proof. My main goals in the sketch were to show you a few things. One is why I need the spaces to be of size less than the continuum. And this was important for the internalizing argument, to get a version of the one colorable sets inside a column hole, a small column hole. Right? And the other point was to show why I need the Malo cardinal. And this is because the internalizing argument kept burning through more and more sizes. And this is the end. So thank you.